Okay, this is going to be 6.3. This is exponential functions. Exponential functions. An exponential function is nonlinear. These are not going to make lines. These are going to grow exponentially. So if I look at something like this, y is equal to 3 to the x, or I could call y f of x. Point being is these graphs are going to have that variable or a variable in the exponent. Now going back to what we were graphing, I told you guys this early in the year, we can graph any function we want with making an XY table or an input-output. Let's just pick some numbers here. Let's go, I'm going to go -1, 0, 1, and 2. Plug in -1. 3 to the -1 power, well, that would be 1 over 3. If it is 0, 3 to the 0 power, anything to the 0 power is 1. If it is 1, it is 3. If it is 2, it is 9. If it is 3, it is 3 cubed, or 3 times 3 times 3, which is 27. These are not linear. This has a constant rate of change. My x is increasing by 1. But remember, to be linear, it has to have a common difference. Here, we definitely have a pattern. But as you can see here, I am multiplying by 3. It is tripling. That's where that 3 comes from. This we call a constant ratio. All of our functions are going to have this. They're going to have this in it. They're going to have some number raised to a power. So an exponential function is nonlinear, and it's going to have this form. Y is equal to AB times the x. Now back to this one right here. My b would be 3. There's my x. My a in this problem is 1. And I want us to think back to this idea of the y-intercept. I know when anything crosses the y-axis, it has an x of 0. Well, anything to the 0 power is 1. This comes out to 1 because there's a 1 right there. Now, if I've got an a in front of here, let's say this is 2 times 3 to the x. Now, in that case, this is going to be 0 because this is not 6 to the x. It is not that. You have to follow order of operations, which tells me exponents first. This is 2 times 3 to the x. And if x is 0, no matter what that number is here, your y-intercept is always going to be multiplied by 1. Your y-intercept is actually a, the number in front of the b. And in this situation, it was a 1 because there's a 1 in front of there. We're going to put a few parameters on this. We're going to say a cannot equal 0 because if it was 0, all of this would be 0. B cannot equal 1, and b is going to be greater than 0. It's not going to be negative. When we plug these in, your y values, what you get out, your outputs form a constant ratio. It's not a common difference, it's going to be a ratio. It's going to be multiplication or division. So here's an example. Here's my x. Here's my y. I'm going to give you some data points. I will go 0, 1, 2, 3. I will go 2, 4, 6, 8. And I'm going to ask you, is it linear or is this exponential? And hopefully you're saying right now that I will be able to tell if it's linear or exponential by seeing if there's a common difference, it's going to be linear. If there's a common ratio, it could be exponential. You're going up 1. To go from 1 to 2, I'm adding 1. From 2 to 3, I'm adding 1. Down here, I'm adding 2. I'm adding 2. I'm adding 2. I have a constant rate of change. This is an addition or subtraction. This is going to be linear. Let's try to write the equation of this. Just given this data, you know it's linear. It's going to look like y equals mx plus b. You need two things to write the equation of a line in slope-intercept form, or y equals mx plus b. I need a slope, or an m, and I need a b, or a y-intercept. Well, I can see that my y-intercept is going to be 2 because my x is 0. So I know I'm going to have a plus 2. My slope is change in y over change in x. Y over x. 2 over 1. It is 2x plus 2. And you could certainly test that. If I plug in 3, 3 times 2 is 6 plus 2 is 8. If I plug in 2, 4 plus 2 is 6. 2 plus 2 is 4. 0 plus 2 is 2. That's linear. That's the equation. Versus something that may look like this, where I have an x and I have a y, and I'm going to go 0, 1, 2, 3. Now I'm going to go 4, 8, 16, 32. And I'm going to look at this. You're going up 1, adding 1 each time on my x's. But my y's know I'm adding 4, now I'm adding 8, now I'm adding 16. Hopefully you can see this is multiplied by 2. It's doubling each time. This is not a common difference. This is a constant ratio. That's a constant ratio. That tells me that it's exponential. That tells me it's exponential. Now, let's write this function with exponential. And remember, we are going to use y is equal a to the bx, because that's what form it has. This b here tells you what that ratio is. So this is y is 2 to the x, because it's doubling each time. In this example here, it tripled each time because that was a 3. So your b is 3 here. That's why this function is 3 to the x, because it's tripling. This problem's a little different because now I have an a value in front of it, because if I wanted to know my y-intercept, if x was 0, I should have a y-intercept of 1. But I don't. I have a y-intercept of 4. Meaning you have to have a 4 in front of it. And I can certainly test this. If I plug in 0, 2 to the 0 is 1. 1 times 4 is 4. If I plug in 1, 2 to the first is 2. 2 times 4 is 8. 2 squared, 4. 4 times 4 is 16. 2 cubed, or 2 times 2 times 2 is 8. 8 times 4 is 32. That is the function that models that one. We're going to look to evaluate. Evaluate each function. And every year, everybody says, this is so easy to evaluate these, but I'm telling you, on the quiz or test, probably 10 to 15% of us are going to forget PEMDAS and forget to follow order of operations. Let me give you this exponential. Y is equal to negative 2 times 5 to the x power. And I'm going to say x is equal to 3. Simply substitute that x in right there. So this becomes y is equal to negative 2 times 5 to the third. Here's where we got to be careful with order of operations. This is not negative 10 to the third. I don't do multiplication before exponents. Exponents comes before multiplication. PEMDAS, parentheses, exponents. Exponents first. Don't laugh because somebody's going to do it. Negative 2 times 5 to the third. Well, 5 to the third, 5 times 5 is 25, times another 5 would give me 125. Negative 2 times 125, well, if I double it, it's 250, and I've got a negative times a positive, so it's negative 250. Letter B. Switch it up a little bit. Y is equal 3. I'll make that b value a fraction, and I'll put that to the x, and now I'll say x is equal to a negative 2. This is where rules of exponents come in. I will substitute that in. 3 times 1/2 to the negative 2. I want to get rid of that negative. We're not going to use negative exponents. I'll take the reciprocal of it. The reciprocal of 1/2 is 2, so this is y is equal to 3 times 2 squared. If I just look at this and I gave you this problem, 1/2 to the negative 2, this would be 1 to the negative 2, 2 to the negative 2. You would flip it. The negative 2 would go away. That's why it's positive. Now I just follow order of operations. Y is equal to 2 squared, which is 4. So 3 times 4, and that equals 12. And I got it. We are going to do a bunch of graphing with these, and this graphing is going to go back using a lot of the stuff that we learned in graphing absolute values. We're going to talk about stretches, we're going to talk about shrinks, we're going to talk about rotations or flipping over the x-axis. But we're going to give some statements here. The graph of a function, and this function is going to be exponential. So y is equal a to the bx, because that's the form our exponential takes on, is a vertical stretch or shrink by a factor of the absolute value of a of the parent function. Y is equal to b to the x. So this is going to go back, take us back to absolute values. Remember, I'm just going to draw this over here. When I had the absolute value of x, y is equal to the absolute value of x. That was our parent function. It was the most stripped down version of our absolute value. It had a vertex of 0, 0, and a slope of 1 on each side. And it went like this. And then, if I put something in there, remember, if I had y is equal to 2 times the absolute value of x, this out front was bigger than 1, so we called this a vertical stretch. It was multiplied by 2. It got steeper, faster. Rise of 2, run of 1. So it was this one right in here. The same thing's going to hold true here. When the number in front of this b is bigger than 1, it's going to be a stretch. It's going vertical faster. And we say it's the absolute value of it because it's still going to be a shrink or a stretch. If this changed to a negative, it just flipped this and made it reflected about the x-axis. Same thing is going to happen with these. When you have a number out front, whether it's positive or negative, if that number is bigger than 1, it's going to be a stretch. It's going to get bigger faster, and that makes sense because if I look at an exponential and how it's graphed, as I go out on the y-axis, if this doubles every time, when I go out to 4, I'm at 64. This graph starts out slow and then it gets fast real quick. Real quick. When a is less than 0, meaning it's negative, it's going to be the same as it is in the absolute value. It's going to be a reflection. So I'm going to say the graph is also reflected about the x-axis. It's going to flip. Here's the important part we've talked about as well already. The y-intercept of y equals ab to the x is a. It's the number out front. And I'm going to think of that for a second. I'm going to look back to that y is equal to 3x. If x is 0, 3 to the 0 is 1. So if x is 0, y would be 1. But this is because this is really 1 times 3 to the x. So your a value is 1. Your a value is 1. If I had something that was like this, y is equal to 4 times 3 to the x, your y-intercept is going to be at 0, 4. It's going to be at 0 and then this number. And I want you to see why though, because if this is 0 here, this is 4 times 3 to the 0. Anything to the 0 is 1, so it's 4 times 1, which is going to give me 4. Your intercept is always going to be the number out front. If there's no number out front, it's a 1. If it's just y is equal to b to the x, your y-intercept where it crosses is going to be at 0, 1. Doesn't matter what's in here. As soon as I take it to the 0 power, it's always going to be 1, and I'm always going to multiply it by a. That is why that is my y-intercept. Let's graph some. Talk through a couple of these. We're going to graph. Certain things are going to happen when I have just this y is equal to ab to the x when b is greater than 1. So when b is greater than 1. I'm going to draw a little XY coordinate plane right here. Here's some curves. And I've got this. When this b is bigger than 1, so it's 1.1, 2, 3, anything, and your a is greater than 0, you're multiplying by a positive number, your graph will look like this. It's going to go up, and it's going to keep increasing exponentially, we say. Now think about it. It's going to come down and it's going to approach this x-axis. Think about the values over here. Let's just say this was y is equal 3 to the x again. And I had this as 1. This was a 3. It's going up fast. But if I start putting negative exponents in here, let's say if x is negative 1, this would be a third. If it's negative 2, 3 to the negative 2 would be a ninth. 3 to the negative 3 would be a 27th. And you can see this is going to get smaller, but no matter what negative value I put in here, negative 5,000, I don't even care what it is. It's going to approach 0. It's going to be real small, but it's never going to be quite 0. That's why it folds this way, or increases this way and approaches the x-axis. Now down below here, this is when a is less than 0. And all that's going to say is when that a is negative, it's going to get negative faster because you're going to have a multiplier there. You're going to take this exponential and multiply it by a negative number. It's going to get negative faster. And it is going to approach the x-axis from this direction. I just want us to always remember, that's always going to be true. Your x is going to be 0, and your y is going to be your a value, and it's going to tell you your y-intercept. So we're going to graph the same thing, but now I'm going to say b is going to be between 0 and 1. Meaning this number right here, what sort of numbers are between 0 and 1? These are fractions. So another little xy coordinate plane here. The graph will get exponentially bigger that way and approach the x-axis from this direction, and it will also get exponentially smaller in that direction and approach. It's going to look something like that. You are still always going to have 0a as your intercept. When a is less than 0, when this is a negative number, it's going to go down. When it's a positive number, it is going to go up. So this is when x is greater than 0. And that's what it's going to look like. It's going to look like this. When b is bigger than 1, when it's a fraction, it's just going to flip and go the other way. Let's graph some. So we are going to graph f of x is equal to 4 times 2 to the x power. And your instructions are to graph it, and you are going to compare to the parent function. We are also going to describe the domain and the range. So here we go. Remember, my parent function is y is equal to b to the x. We said that on the first page. So your parent, and I'm going to call that, instead of f of x, I'm going to call it g of x. That is just going to be this 2 to the x without the 4. That's the parent function. That's what I'm comparing it to. The 4 is the a. To find your parent function, you get rid of the a. What's left? That's your parent. That's what we're describing it to. If I look back at f of x here, this definitely looks like y is equal to ab to the x. And I can look right here. This b value is greater than 1 because it's 2. And your a value is greater than 0, it's going to look like this graph right there. Here's some steps we can use to follow to graph these. First step, make a table. Second step, plot ordered pairs. Nothing's going to change from what we did before. We need to plot our ordered pairs. Third step, this is a curve, and you want to make a smooth curve. We want it to look good. It'll take some practice to get these to draw. And then we're going to describe it. So the first step, make a table. And if I look right here, I'll be able to find my y-intercept. If I choose some negative values of x and some positive values of x, it's going to give me an indication of what's happening here. I'll be able to see that it approaches the x-axis. I will be able to see that it gets exponentially bigger as I go up. What values would be handy to choose? Well, certainly some negatives and some positives, and that's what I'm going to choose. I'm going to choose -2. I'm going to choose -1. I'm going to choose 0. I'm going to choose 1. And I'm going to choose 2. And I can easily get my x-intercept because my y-intercept, because if I let x equal 0, I know that my y-intercept is a, which is 4. But I could also plug this in. 2 to the 0 is 1. 1 times 4 is 4. Now, yes, I can certainly plug these in, but I can also use my brain a little bit going forward. Remember, this 2 tells me what that ratio is. It's telling me it's going to double. 4 times 2 is 8. 8 times 2 is 16. I knew that because of that 2, but I could easily plug in 1 for 2. I'm sorry, 1 for x. 2 to the first is 2. 2 times 4 is 8. If I plug in this 2 for this x, 2 squared is 4. 4 times 4 is 16. And I've got it. Now to go in the other direction, instead of multiplying, I would just divide. This would have to be 2. This would have to be 1. I can certainly plug -2 in. If x is -2, that would be 1 over 2 squared, or 1/4. 4 divided by 4 is 1. Yes, you can plug these in. I'm not going to plug them in. I'm going to find my y-intercept, and I'm going to use this b value to figure out what my ratio is, and then perform the math in both directions to get points on either side. X is going between -2 and +2. Y is going up to 16. I think I will make my xy coordinate plane here. I know I don't have to go very far down because it ain't going to be below this x-axis here. I should carry this out to a -2 at the minimum. This would be -2, -1, 1, and 2. I'm going to go by 2's here. 2, 4, 6, 8, 10, 12, 14, 16, 18. Call that my y. -2, 1. To the left 2, up 1. -1, 2. 0, 4. 1, 8. 2, 16. And I could see if I was at 3, I'd be at 32, somewhere up here. It's going up in this direction, and I would expect it to go in that direction because that b value is greater than 1 and a is greater than 0. It is going to approach the x-axis but never quite get there. This is f of x. To graph g of x, this is my parent function right here. You would have a y-intercept of 1 because if x is 0, this would be 1. 1 times 1 is 1. And I'm just going to put some points that are really easy in here. If x was 1, it'd be 2 to the first. It'd be 2. If it's 2, it would be 4. And you can see it's going in this direction. If it was at -1, it would be at a half. If it's at -2, it would be at a fourth. And you can see as I get smaller with my negatives, it will absolutely approach that x-axis but never cross it. This is g of x. This is the comparison we need to make. How does f of x compare to g of x? We know this is getting steeper faster because it's got that 4 out front. This is a vertical stretch. It's getting more vertical faster. It's a vertical stretch. By 4. I'm going to say something about the y-intercept. The y-intercept shifted. It either shifted from 4 to 1 or it shifted down 3. I could say the y-intercept shifted down from 4 to 1. I could say it went down 3 from 4, as long as we compare them. Your domain, remember, refers to your x's, and as I go out on the x-axis, yes, it's approaching this x-axis, but it's never quite getting there. There's not going to be a value for the negative x's, that's not included. And this is going to go on forever in this direction. This is going to be all real numbers. Your range, though, your y's, you are not going to be above the x-axis. You are not going to be below the x-axis. All the y's are above. You want y's that are greater than 0. Remember, that's the line y equals 0, the one that lies on the x-axis. Horizontal line going through 0. We want y's that are greater than 0. Let's look at another one. This is a graph. Y equals AB to the x. But now I'm going to make that b be a fraction. It's going to be between 0 and 1, meaning my graph is going to shift like this. It's going to look like this when that b value is between 0 and 1, when that b is a fraction. So here we go. F of x is equal to, let's say, negative 1/2 to the x power. And we're going to compare it to our parent function, and we're going to state the domain and range. Your parent then, which I will call again g of x, is just going to be this without the a value. Well, your a value in this, since this is negative, remember that's really a -1. So your a is -1. This inside here is what your parent function is. G of x is 1/2 to the x power. Step 1 said make a table. Let's make a table. And again, what I am going to do is pick that 0 and a couple numbers above and below it. I'm going to get my intercept. So for f of x, right here, it's going to be my a value, which is -1. Or I take 1/2 to the 0 power, which is 1, and I multiply it by -1, it still gives me -1. This is what I multiply by to get my ratio. -1 times 1/2 is a -1/2. Then if I multiply this, it is going to be a 1/4. Or if I put 1, or if I put 2, it is going to be a -1/4. To go in the other direction, you just multiply by the reciprocal. If this is -1, even if I put a -1 here, this is -1/2 to the -1. I would take the reciprocal of it to get rid of it. The reciprocal of 1/2 is 2, and I multiply it by a negative, it's -2. If I use -2, it would be -1/2 to the -2. This is going to be a, flip it, 4 times a negative, it's going to be -4. And you can certainly check it. If you use this b, half of negative 4 is negative 2. Half of negative 2 is negative 1. Half of negative 1 is negative 1/2. Half of negative 1/4 is, or half of negative 1/2 is negative 1/4. And I got it. Let's graph it. And I'm going to graph f of x first. And then I'm going to graph my parent function. Here's your x. Here's your y. I'm just going to go by ones. So on this one, I have 0, negative 1, which is right there. 1, negative 1/2, right there. 2, negative 1/4, right there. Negative 1, negative 2. Negative 2, negative 4. And you can see that your curve now is just flipped going in this direction. What made it flip is that fraction, when that b is between 0 and 1. This is f of x. To get g of x, I'm just going to use the 1/2. It's going to be the exact same thing, except what? It's going to be flipped. Your y-intercept is going to be a positive 1. Now, if it's a positive 1, 1/2 to the 1 is 1/2. If it's 2, it's to the 4th. Now, if I go in the other direction, I take the reciprocal. So if I'm at negative 1, it's going to be at 2. If I'm at negative 2, it's going to be at 4. This curve comes down like this and approaches the x-axis in that direction, and that's g of x. These are the two that we want to compare. First thing I see right away is because one is negative and one is positive, this is an absolute reflection. This is flipped over. I'm going to say reflection about the x-axis. The intercept is certainly shifted. You could say y-intercept shifted from negative 1 up to a positive 1. And if I look in front, there's no value in front. 1 is negative, 1 is positive, but there's no number in front of here. It's both the same. They're both 1. What the negative did was flip it. There's no stretch or shrink in here because I looked to the a value to decide that. Up here it was 4. It was a stretch. If it was 1/4, it'd be a shrink. Here it's exactly the same, except one is positive, one is negative. That flips it. Your domain is going to be your x's. It's going to be all real numbers. Your range, which is your y's. If I look at my y's, it is going below the x-axis. This one, you want not y's that are greater than 0, but y's that are less than 0. And there we go. Okay. Last little section. Now we're going to amp it up just a little more. This is going to be to graph y equals. Now we're going to add some stuff to it. Just like before, remember our parent function was y equals b to the x. Then we added an a in front of it. Now we're going to make it where we're going to add something in the exponent. And we are going to use those K and those H's again. The K now, just like when we did absolute values, when it was inside that absolute value, the opposite of K and H, that told us our vertex when we were in vertex form. And this will do the same thing. These are going to shift it. They're going to shift it. So to graph it, when I have this exponent plus or minus something and then something added on the back, we start by graphing y is equal ab to the x. We start by graphing that, and then we can see what's going to happen when these shifts. Then we're going to translate it. We're going to shift it. Translate the graph horizontally, meaning it's going to shift over, right or left. K units, this is my left or right shift still. And it's going to shift up or down or vertically, K units. Sorry, this is horizontally H units and vertically K units. I did not switch them. So here's my example. Graph y is equal to -2 times 3 to the x plus 2 minus 1. We are also going to describe domain and range. First thing you're going to want to do in this, start by graphing the parent function, y equals ab to the x. It is this right here, -2 times 3 to the x. Because if we want y equals ab to the x, I take everything that I see there and I'm going to leave off that k and that h value. So this is y is equal to -2 times 3 to the x. That's what we're going to start with. So, if I make a table, I have an xy. I'm going to choose my values that I know are easy to work with, and I know that if I have an x of 0, this is a -2. And I can certainly use this 3 now as my multiplier. If I'm going in the right direction, in the direction to the right, I multiply it by 3, it'd be -6, and then this would be -18. And I can certainly plug that 2 in there and check it. 3 squared is 9, 9 times -2 is -18. To go to the left of my y-intercept though, I don't multiply by 3, I'd have to divide by 3. 2 divided by 3, that's a -2/3. And then I would do it again, dividing by 3, multiplying by 1/3, -2/9. This is what we got. Start by, this is what I needed to graph to start out. Here's what I'm looking to graph now though. Remember, this is going to be my shift. It shifts -2, the opposite of h, which is right there, and it's going to shift 1 on the y because it's -1. This is what I switched. I knew I switched something. The horizontal is h, vertical is k. I switched them up here when I wrote it. This is going to shift -1 on the y. So here's what I can do. I can make another little xy table. And I can certainly plug in the same values. Now I want us to just look like kind of what's going to happen here. What's going to happen here? Everything is going to be shifted. Everything is going to be shifted. If I just plug in these numbers right here, -2 for x, I'm just going to plug these in and get some values. -2 plus 2 is 0. 3 to the 0 is 1. 1 times -2 is -2, and then I would subtract 1 is -3. If it's -1, it would be -1 plus 2. -1 plus 2 is 1. 3 to the first is 3. 3 times -2 is -6. -6 minus 1 is -7. If it's 0, 0 plus 2 is 2. 3 squared, 9. 9 times -2, -18. Subtract 1. -19. If it's 1, that makes this 3. 27 times -2, -54. Subtract 1, -55. And I could keep going. That 2 is going to be a bit big. You see it's getting exponentially smaller, though. If this was 2, it would be 4. 3 times 3 would be 81. -162. Subtract 1, -163. Doesn't matter, I'm not going down to -163 anyway. You can certainly plug it in and get it from there. What I want to show you is how this shift would work down here. I'm going to take these numbers right here, and I'm going to use this shift now. So I'm going to make an XY table, but now I'm going to look at my x's. And when I take my parent function, I get values out. All I got to do is shift this 2, shift my x's by -2, and shift my y's by -1. So I need to just take my x's and subtract 2 from them. So if I'm at -2 and I move another -2, that's going to be a -4. If I'm at -1 and I shift to the left -2, that would be -3. If I am at 0 and I shift, that would be -2. If I'm at 1, it would be -1. And if I'm at 0, or if I'm at +2, 2 subtract 2 is 0. All I did was subtract 2 from each of these numbers. Negative 2 minus 2, negative 4. Negative 1 minus 2, negative 3. 0 is negative 2. 1 minus negative 2, negative 1. 2 minus 2 is 0. Now all I got to do is shift this to the right. Or I'm sorry, to the left, negative 1. This is negative 1 in 2/9 because I just take negative 2/9, subtract 1. Negative 1 in 2/3. I just take negative 1 and subtract 2/3. If I plug in negative 2, negative 2 would give me a negative 3. Negative 1 would give me a negative 7. Negative 18 would give me a negative 19. And again, all I did was take this parent function, subtract 2 for my x's, and then subtract 1 from my y's, and came up with these new ones right here. Time to graph. Here's my x, here's my y. I'm going to go by 5s. Now my x's, I'm just going to go by 1s. Negative 1, positive 1, 2, 3. And let's graph. I'm going to graph this one right here. Negative 2, negative 3, somewhere right about there. Negative 1, negative 7, somewhere right there. 0, negative 19, right there. There's my y-intercept. 1, negative 55 is going to be somewhere down there. And then that 2 was negative 160 something. Doesn't matter. What matters is, hopefully you can see that as you go this way, it's approaching the x-axis here. And this is coming down and going in that direction that way. And look, I got some of the same points here, whether I plug it in or not. So it doesn't matter that I'm going negative 4, negative 3. All this is telling me is as I go out here to this negative 4, I was only at negative 2, I was at negative 3. But if I go to negative 3, I can see right here, it's getting closer to the x-axis. I don't care how we graph them. We just got to be able to graph them. You could certainly just plug those in, or you could use your shift. The domain of that one, this function right here, is going to be all real numbers. Your range, though, it is not going to approach the x-axis. As I look here, it's going to get really, really close to this negative 1. But it's not going to cross it. Here it doesn't approach the x-axis because you're always subtracting 1. It's going to approach the line negative 1. You want y's that are less than negative 1. How do you tell that? You look right there at your vertical shift. If that's a negative 1, that's what it approaches because you're subtracting 1 each time. There you go. That is everything in a nutshell. These take some practice, and we will certainly work through these.